Swayam Prabha. Digital India. Educated India.
So what we will be working with is basically points in RD. So, okay, so not d equal to 2. So most of the things that you have seen in the first few lectures. Okay. So we will be learning tools like techniques these classes, so that which will help us trying to prove duality theorems that Arijit Vishnu was mentioning last class, okay, for Delaunay and Voronoi diagrams and convex cells. Okay. So as I said, we will be working in RD. Up till now what we have seen is for d equal to 2 and 3, but we will be work with general RD. Okay. So few basic facts. Okay. So let's do that first. Basic facts that I will be using. Okay. First, okay. So if I give you, let's say, d plus 1 vectors all in RD, okay, will they be linear? Can they be linearly independent? No, right? Okay. So size of a basis is what in RD? Basis of vectors will be d. So any d plus 1 vectors if I take, if I give you d plus 1 vectors, so there exist constants C1 to CD plus 1, not all equal to 0, not all zeros, such that we will have this will be equal to 0, right? Everyone with me when I say this? Good. Okay, so let me give you, let's say, k points. So let me use points, p for points in this lecture. So k points in RD. Okay, k greater than equal to d plus 2. If you have k points where k is greater than equal to d plus 2, okay, what will be the dimension of this plane or dimension of the space containing these k points? So let's say, forget about this, let me make this change one side. So let's say k is less than, let's say, call it less than equal to d. Okay. What will be the dimension of the plane or hyperplane or a flat that will contain all of these points? What will be the maximum dimension? Yeah, so it can be a hyperplane d minus 1, okay, because I am taking k points, k less than d, but there should exist a flat. Okay. Flats are generalization of lines and hyperplanes in R3, right? K dimensional flat, that k minus 1 dimensional flat that contains this k points. Okay. So these basic facts we will be using. Mostly these are the only things we will be using in this class. Okay. Okay. So let me give you some definitions. So what is something called affine combination? Okay. So let P1 to Pn be n points in RD. Okay. We define affine combination of these points in the following way. It will be summation define affine combination, right? So points that we get by taking combinations like this, where summation Ci is equal to 1. Okay. That is what we define as affine combination of points. Okay. What will this give you? This will give you the smallest dimension flat that contains these endpoints. Okay. It may end up being whole of RD, or it may be a hyperplane in RD. So, a flat of dimension d minus 1 or a flat of dimension d minus 2. This is something we do not have to worry. Okay. Okay. This combination will generate all the points that will lie on a flat, and that flat will be a smallest dimension flat that contains all of these endpoints. Okay. I am not enforcing non-negativity of Ci also. Okay. It's clear? Okay. Good. So, let us go to definition 2. Okay. What is a convex combination then? Again, we have endpoints. Okay. No, I am saying for affine combination it does not have to be positive. So, the question is, does Ci have to be positive or non-negative, let us say. Okay. No, they can take any value, summation should be equal to 1, that is it. Pardon? Yeah, sum to 1, that is it. Is it clear? Yes. Oh, okay. So, let us so do you know, so I do not want to get into formal definition of it. So, let us say you are in R3. Okay. What are the flats in R3? Okay. A point is a 0 dimensional flat in R3. Okay. A line is 1 dimensional flat in R3. Okay. A plane is a 2 dimensional flat in R3. Okay. And the 3 dimensional flat is R3 itself in R3. Okay. And you can generalize this in higher dimensions also. Okay. So, what about convex combination of these points? How do we define it? Same, only thing we ensure is Ci has to be greater than or equal to 0. That is it, no more. Okay. So, what does this set gives you? So, as I said, if I take all affine combination, I will get the smallest dimension flat containing these points. Okay. By the way, smallest dimensional flat containing a set of points is also unique. Okay. So, this is something to check. Okay. Check this when you go back. Okay. Is it unique? Try to go and prove that it is unique. Okay. Again, go by the analogy. Okay. So, let us say you have some points in R3, okay, and these points lie on a line. All of them lie on a line. Okay. Can there be, and so number of points, let us say, is greater than or equal to 3, 4, whatever. Okay. 5 points all lying on a line. Okay. How many lines can be there other than the line that goes through this point that contains all of these 5 points? Can there be more than one line? It is unique, right? Similarly, you can prove for in the higher dimensional case also. Okay. The same proof works actually. Okay. You have to do slight amount of vector space analysis, that is it. Okay, good. So, now if I ensure Ci is greater than or equal to 0, what do I get? We get what is called convex combination of points. Okay. So, I am varying Ci's such that all Ci's are greater than or equal to 0, but they sum up to 1, okay, and I am looking at all the combinations like these. Okay. Ci-Pi summation. Okay. This is what is called convex hull of the points. Convex hull. Convex hull of the set which is the smallest convex body containing these points. Okay. Again, this is unique or not unique? Good. Okay. Again check these things. So, once you define affine combination, it is natural to define what is called, what is the affine dimension of the points, or are given a set of points, are they affinely independent? Okay, okay, affine independence. So, in vector space we have this notion, right, dependent set of vectors, independent set of vectors. Same thing holds for affine independence, affine dependent case. Okay. Again, so let me just give you, like, there are number of ways to define it. One way to define it is, let us say I am looking at, so let me denote by AFF of P affine combinations of all the points in the set P. Okay. So, the set P contains P1 to Pn points, f of P will define affine combination of this point set. Okay. I will say the point set P is affinely dependent. If you have two different representation of the same points inside P. So, what do I mean by that? Okay, what do I mean is, there exists a point x in this set f p such that I can write x as summation C I P I, and there will be a separate set of constants C I prime, and I can write x as C I prime P I also. This set C 1 to C n and C 1 prime to C 1 C prime n, this set, okay, they should not be same. Okay. I mean, should not be same in the following sense, I mean, like C 1 should not be equal to C 1 prime, 1 to 1 they should not be equal, this should not be the case. There should exist at least one index I such that C I is not equal to C I prime. Okay. Same analogy as vector spaces, right. We had, if the vector space is linearly dependent, there will exist a vector in the span that will have two representation, right, exact analogy. Proof exactly same, exactly same. Okay. So, now a set which is not affinely dependent will be affinely independent. Okay. So, so these basic things we need to begin the begin what we will be covering in this class. Let me check what I wanted to do. Okay, so what is our goal? Okay, so I want to cover three theorems. These are three fundamental theorems in convex geometry, widely used in computational geometry, in discrete geometry, in convex geometry theorems. Deep theorems in convex geometry also uses these simple results that we will be proving today. Okay. One is Radon's theorem, all of them named after different people. Helly's theorem, and then another one is Carathéodory theorem. There are some accents which I do not remember over the alphabets. Okay. These are the three things I want to cover. Okay. Let's try to prove Radon first. Okay. Using Radon, I will be proving Helly's theorem. Okay. Good. How do we get it down? Okay. So let me give you the statement of Radon's theorem. So, given a set of a set A of D plus 2 points in R D, okay, there exist two subsets, two disjoint subsets A1 of A such that their convex hull intersects. Convex hull of A1 intersection. So, I will denote by conv of a set as the convex hull of the set. Okay. Okay. I am saying the convex hull intersects. Can this set itself be empty then? What is the convex hull of an empty set? Not defined, I mean it is an empty set itself, right. What combination are you taking? So, this means when I say disjoint, see a disjoint set, this set let us say if I took it to be empty and this to be A, okay. These will be disjoint sets, right. Intersection of A1, A2 is disjoint, empty set, right. But when I say this, that means they A1 and A2 are disjoint and non-empty. Okay. So, we will be proving if you have D plus 2 points, okay, inside this D plus 2 points I will find two disjoint non-empty sets whose convex hull intersects. Okay. This will be plain application of the concept of linear dependence, direct, nothing special than this. Okay. So, let us see the proof of this. Is it clear, the statement of the theorem, everyone? Okay, good. Again, if you have some doubts, so let us say I call this set A, like the points be A1, okay. I have D plus 2 points. Are they affinely dependent or affinely independent? Pardon? Affinely dependent. Okay. What did I say? If they are affinely dependent, there will be an x such that will have two representations. Okay. That is one definition. There is another definition, and you try to show equivalence between the two when you go back. Okay. Another definition is, since this D plus 2 points, since that D plus 2 points in RD, they are affinely dependent, I will say there exist constants C1 to CD plus 2, again not all zeros, such that, so ST means such that, okay, such that summation Ci AI I equal to 1 to D plus 2 is equal to 0 and summation Ci is equal to 0. Exactly, why I did this. Okay. So, let us first let us do this exercise, it will be a good exercise for the rest of the course also. Okay. So, there was one definition of affine dependence, right. I have given another one and I said these two are equivalent. How do you prove it? These two are equivalent. See, when I said affine dependence, I said there exists a point x in the affine hull of A such that it has two representations. So, I can write x as summation Ci Ai I equal to 1 to D plus 2 such and summation Ci is equal to 1. It has another representation also, which is summation Ci prime Ai and summation Ci prime is equal to 1. These two are equal to, right, this is equal to this representation of same points. Now, can you see the why this gives you the top thing? I take this terms from here and bring it here. Okay. What does this equal to implies? Equal to implies that summation Ci minus Ci prime Ai I equal to 1 to D plus 2 is equal to 0. This is something we already have, I mean this is something I was already mentioning here, But there is another thing I needed. I said this should be equal to 0. Observe, if I add C I minus C I prime I equal to 1 to d plus 2, this is also equal to 0. Why? This is equal to summation C I minus summation C I prime, each is equal to 1. Okay. So, that is why they are equivalent. You can go back and forth with this definition. If the number of equivalent definition, always use the definition that helps you prove the theorem in a more succinct way. Okay. Good. So, now, so again, so we have this. So, let us go back to the proof. So, we have C I A I equal to 1 to d plus 2. Okay. This is equal to 0 and we have summation C I equal to 0, I equal to 1 to d plus 2. Good. As I said, all CI's cannot be 0. There are some positive and there has to be, if there is some positive, then there has to be some negative. Okay. So, by definition there are positive and negative terms here, right. Good. So, let us say I make a set A1, and by the way some can be 0, what I am saying is not all cannot be 0. Okay. Let us make a set A1 where all the AI's such that CI is greater than 0. Make a set A2. How should I define A2? Less than 0, right? What can we say about this set? One thing I can say is summation Ci where Ai belonging to A1 has to be greater than 0, right. Similarly, this one will be, if I take summation Ci Ai belonging to A2. So, I am adding up those Ci's that belongs to A2, where Ai belongs to A2. This has to be, but they have to be exactly opposite sign. Okay. If this is, if I say this value is S, so this value will be minus S, because they have to sum to 0. Okay. So, now we have already we have a proof of this theorem that we wanted to get. How do you do it? Consider the point x, which is equal to summation Ci by S. So, summation Ci here is S, where Ai belongs to A1. This point belongs to where? Convex hull of A1. Why is that? If I sum of these terms, it turns out to be 1. All of them are positive. So, this point x belongs to convex hull of A1. But by construction also, this I can write it as, this is equal to summation minus Ci by S Ai, where Ai belongs to A2. Can everyone see this? A2. Okay. Why is this the case? My claim is this is also true. Summation over A1 is okay, it belongs to convex hull, but I am saying x is equal to this also. Oh, so let me go to the other page. I think it is getting it's getting. So, I am saying x is equal to, I am defining x as summation Ai belonging to A1 Ci by S Ai, and as we said that this is okay. This belongs to convex hull of A1. Okay. My claim is, this is a claim. Okay. Is this x, I can write it as this also, minus Ci by S Ai, where Ai belong to A2. It's true, not true? Why is this the case? By the way, let us say this is true. Okay? These terms are all greater than equal to 0. Actually, these terms are greater than 0, right? Because these Ci's, since ai belong to a2, Ci's are negative. Minus over negative is a positive term, right? Okay. So, this belongs to, so this, and if I sum it up, this will come up to, if I just sum it up Ci's where ai belong to a2, it will have come to minus s. So, minus of that will be s, and s by s is 1. So, this belongs to convex hull of a2. So, if I can prove this part of the claim, the proof is complete. I get a point x which we call as a witness. Okay. X is a witness here. What is it witnessing? Like a legal term, right? It is witnessing that the convex hull of the two sets are non-empty. We have a certificate. There, like in NP completeness, we have these terms, right? Certificate. The term witness is also used sometimes. Okay. It tells you that this is the point that lies in the convex hull of both of these points. This itself shows that the convex hull are not disjoint, they intersect. Good. Okay. So, now we will look at this. How do we prove this? So, see, up till now, up till what I have written now in the proof, have I used the fact, so one, I have used the fact of linear dependence in the place where I use there should be some Ci's that have to be positive, which implies there will be some Ci's that have to be negative. That is one place I have used the linear dependence property. Here I will use it another time. Okay. See, we know summation Ci ai I equal to 1 to d plus 2 is 0. Now, I will partition this set A into 3 parts. I write this is equal to summation ai belonging to a1 Ci ai plus summation Ci ai where ai belongs to a2 plus all the ai's that lies outside these two, right? A minus a1 union a2 Ci ai. So, let me Ci ai, and I know this term is equal to 0 also, right, because this is basically writing, this is one way of writing this thing. Right. I know this is equal to 0, so this has to be equal to 0. So, this thing has to be equal to 0. I know this is equal to 0. Why? Ci's have to be 0, because if Ci was positive, then that point ai would have been in a1. If it was negative, then it would have been in a2. What are the things that are left? Whose coefficient Ci's has to be 0. So, 0. So, we get this plus this is equal to 0. Now, rearrange and get the equality above. Okay. Now, complete the proof. Complete the proof from here. Okay. Good. Okay. So, this is equal to 0. This term is equal to 0. Right. This I have written it in this way. Right. As a summation of 3, this one summation I have written in terms of 3 summations. One where the indices are going over the points in ai, one where the indices are going over points of a2, one where the indices are outside this a1, a2. Right. Since this is equal to 0, this term is equal, this summation is equal to 0, this is also equal to 0. But look at the third term. Third term is I am saying is equal to 0. Third term is not just summation equal to 0, term by term equal to 0. Why is that? See, if your Ci's corresponding to the ai's where ai lie outside a1 and a2, okay, those Ci's are 0. If it was positive, then that ai would have been in a1. If it was negative, that ai would have been in a2. then there each Ci is a 0, so this term is 0. See, I want the a point in the convex hull of these two sets, right? A convex hull, what are the points? So again, so go back to the definition of, let me go to page where did I define? So how do we define convex hulls? Convex hulls are the points of the form Ci Pi. If let us say the set is P1 to Pn, then the convex hull is of the form summation Ci Pi, right? Where summation Ci is equal to 1 and Ci is greater than equal to 0. So I need Ci greater than equal to 0. That part was there, even if I don't divide it by S, but I want the sum to be equal to 1. That why I need this normalizing term S. So S is a normalizing term. No, I am not see, that is exactly what I don't want to prove. I don't want to prove the convex hull of A1, A2 are disjoint. I want them to intersect. What I want is the set A1 and A2 to be disjoint. Set A1 and A2 is disjoint, right? But the convex hull is intersecting. Oh, okay. So let me go back to the. So I build a set, I build a point x, right, in this way. Summation. So the question is, how do we show that the convex hull is not disjoint? Okay. So I said I will make a certificate, a point that lies in both the convex hull. What is the point? So let's first make a point in A1. How do I do it? I do the following combination: summation ai belonging to A1, Ci by S times Ai. Is it clear why this term belongs to the convex hull of A1? Because summation Ci, where Ai belongs to A1, is equal to S. So if I add up summation Ci by S, Ai belonging to A1, that turns out to be 1, and Ci's are positive. Okay, so this point belongs to the convex hull of A1. We have also shown that this summation can be written in the following way: summation minus Ci by S Ai, where Ai belongs to A2. Yeah. So let's look at this top equation again. This one equation. So let me use a different color. These equations again. If there was no S present, and let's say there was no X, I have already shown equality between these two terms. Now I divide both sides by S. If I divide both sides by S, then this point, once I divide, so once I bring in S, this point will belong to the convex hull of A1. Once I bring in S, this point will belong to the convex hull of A2. So that is why they are. I found a point that lies in the convex hull of both the points. Okay, so one thing you can try, can you think of some other generalizations? Other generalizations of this. I will be playing again with this simple linear independence. I will slightly try to generalize. So one way to think is, I want to get a similar result where rather than showing convex hull, so see, the convex hull was defined as summation Ci Ai. So let's say of set of points A, let's say A1 to An. So I define convex hull as summation Ci Ai equal to 1 to N, with the property that all Ci's for all I, Ci is greater than equal to 0 and summation Ci is equal to 1. So this is how we define convex hull. I want to remove this term. I don't want to take this term. I don't want to write summation Ci is equal to 1. I only ensure Ci's are greater than equal to 0. try to think of a theorem. This will be a good exercise to think of a theorem. Can we prove something similar to what we have proved for Radon for convex set for these kind of sets? These kind of sets are called cones. Why is it called a cone? Let us say look at an R2. So, let us say you have a point P1 and you have a point P2. Okay. If I take combinations of P1, P2, but the coefficient of the combinations are non-negative, I will generate all the vectors inside this cone. So, can we think of a theorem for these cones? Try to think whether we can get something here. Okay. But we want to play with this simple affine dependence independence game only. Do not want to do something deep. If you want to do something deep, you can obviously welcome, but try to play this simple thing. Just for cones, can I say something? Yes. So why d plus 2 is required? Okay. So, let us say I make it d plus 1. What happens? Does read d plus 1, is there a problem with if I take d plus 1? I took d plus 2. So, the question was that I have assumed the size of the set is d plus 2. The set is in RD, size of the set is d plus 2. What happens if I take d plus 1 points? See, there exists d plus 1 points in RD that are affinely independent. See, when I say affine dependence and vector space dependence independence, the same thing. How do you show that? So, it is good. So, let me go slow and just make that connection more clearly. Okay. So, let us look at again the definition of, as I said, always use a definition that suits your purpose. Okay. So, how do we define affine dependence of a set of points? I said, okay, if you have a set of points A1 to An, let me purposefully write it as A0 to N. Okay. We will see why. Okay. I have some set of points and they are affinely dependent. The definition I want to work with is summation Ci. So, there exist, if they are affinely dependent, then there exist Ci's not all equal to 0, such that Ci summation from 0 to n Ai is equal to 0 and summation Ci is equal to 0, I equal to 0 to n. This was a definition, one definition for affine dependence, right. So, now I want to say that I want to connect it with another thing. Okay. Rather than looking at this n, so this is there are n plus 1 points, right. It starts from A0 to n. Okay. So, let us do, I will build some set of vectors from these points. Let us build some vectors. Vectors will be from V1 to Vn. So, what will be Vi? Vi equal to Ai minus A0. This is what I am doing. Is it clear what I am doing? So, I will get how many vectors? N vectors. So, my claim is if these vectors are not independent or these vectors are dependent vectors, then the corresponding set of points A0 to N will be affine dependent. If this set of vectors V1 to Vn are independent vectors, the top one will be independent also. So, I will give you one connection. So, let us say they are dependent. What does that mean? Suppose they are dependent, what does that mean? No, that is not. So, let us take the simple. What is so? It is just simply there exist. See again some constants di. not all 0, such that di vi is equal to 0. Yes, no, maybe, right. So, if this is dependent, this set of vectors is dependent, then I can find di's such that for I equal to, see it goes from 1 to n, okay. It is important. No? I have taken a naught to be the hinge, I have moved the origin to the a naught, okay, and then I build these vectors. Okay. So, I can find di's for which this is equal to 0. What does this mean? So, I will write it in terms of ai's again. So, this means summation di ai minus a naught I equal to 1 to n is equal to 0. Can you see the ci's that I will get here from this? What are the ci's? Come again. So, now my claim is take ci to be equal to di if I for I 1 to n, and take c naught to be minus of summation di's. I will get this, right. I have found some set of ci's, again not all equal to 0. How am I getting not all equal to 0? Because some of the di's are not equal to, has to be not equal to 0. So, I will find not equal to 0 ci from here itself, from 1 to n itself. This may be equal to 0, I do not care by the way. I need to find 1 at least, that is good enough. What is an IJK? I didn't get it. You, okay. So, okay. So, okay. So, what is asking is in 3D. So, my 3D drawing skills are quite bad. So, should I say x, y, and z? So, that kind of rule, whatever is the notation. And he is saying I take one. This is the I vector, unit vector. Does it matter if it is a unit vector? So, a vector aligned along x axis, a vector along y axis, and a vector aligned along z axis k. Are they dependent or independent in R3? They are. So, verify. Can I write as a, can I write, so see, I mean again since you wanted your favorite vectors are unit vectors. So, take I to be 0 0 1 0 0, sorry. This one is 0 1 0, this is 0 0 1. Can I find ci's, c1, c2, 3 vectors, 3 constants such that summation, so let me write hat I1, I hat, j hat, k hat. So, c1, so let me write c1 I hat plus c2 j hat plus c3 k hat equal to 0. Can I make it like this? What will this give me? This will give me c1, a point c1, c2, c3, a vector c1, c2, c3. For this to be equal to 0, c1 has to be 0, sorry, c2 has to be 0, c3 has to be 0. Another vector. Yeah. So, okay. So, okay. So, I mean I cannot get into elements of vector space here, but let us say I am in RD, in any RD. Okay. What will be the dimension of a basis set in RD? So, what is a basis set in RD? Set of vectors that are linearly independent, but spans whole of RD, right? That is RD. Okay. In this basis set, if I add one more vector, will the set remain independent? Why does it not remain independent? Pardon? Can you come again? Yeah, I mean again that one way to see it, but another way you will have two representation of the same vector again. That vector itself, and that vector can be represented as a representation of these vectors also. And if I include this inside here, I will have a vector which has different representation in this set. Okay. See, you do not have to do it like this. I want to stress this point because this is something I will be using, right. That is why I am trying to stress. This is another way to look at these things. Okay. So, okay. So, let me give you some equivalent kind of statements, okay, and try to check whether you can prove these are same or not. Not many, I will give one only, just check. This is like a theorem 2, equivalent statement. Huh? What did I say? I started with a set of d plus 2 points in RD. Okay, and you said that, okay, Radon's theorem says you can find two disjoint sets, subsets of A such that their convex shall intersect. I want to give a separate thing. I want to say I can partition the set A. There exists a partition of A into two disjoint sets A1, A2 such that convex hull of A1 intersection convex hull of A2 is not equal to empty. I want to prove this. Okay? I won't prove this as an exercise. Go back and see, just using the previous one we can get a proof for this directly. These are equivalent statements, by the way. See, A1 union A2, I said A1 A2 are disjoint, but in the previous thing I did not say A1 union A2 is the whole of A. Now I am making some slightly stronger claim. This is an apparently looking stronger claim. It is not a stronger claim actually. Okay? These are same statements. Good. Yeah, disjoint. So I don't know, there are people use kind like this notation sometimes. I don't know. I mean, like, you understand what partition? Partition means union. So I will say a collection of subsets of A is a partition of A if union of those subsets is A and the subset should be pairwise disjoint. Okay. So I wanted to prove Helly's theorem, but since I don't have much time now, I will prove a, pardon? Whatever makes you happy. How do you write partition notation? You can say. So by this I mean union of A1 A2, but this notation means A1 and A2 has to be disjoint. Rather than writing this, I am using one notation. That's it. Okay. So I mean I want to do Helly's theorem. Let's defer Helly's theorem for the next session. Let's look at one very simple application of this result, which has been, it is one of the most, even though it is very simple, it is one of the most fundamental objects in convex and not convex, in mainly discrete geometry. Okay? There is a concept of VC dimension which Rajiv will introduce, but I want to play a small game with it now. Okay? I will want to do so let's say, so one example I want to do using radon. So even though this example is an apparently an extremely simple thing, this is an extremely fundamental observation that is used everywhere in theory of set systems. For theory of especially set system with bounded VC dimension. Again, I am not defining what is a bounded VC dimension or what does VC dimension mean for a set system. Rajiv will do it next week, but just as an introductory example, let us work on one thing. Okay. So what I want to do is, I want to do the following. Let us say I give you a set S of points in RD. Okay. Now what I want to do is, I want to generate all subsets of these points S in some way. So how do I do it? So let us work with d equal to 2 case first. Okay, so I have some, let me use a different color. I have some set of points. So, I will say a subset S, so subset S1 of S can be generated by a line in R2 if I can separate S1 from the rest of S. So, I want to separate S1 and S minus S1 by a line. So, let us say the set S1 is this 3 points. Okay. I can find a line that separates these two. Okay. So, this means this is a set S1 I can generate from S. Okay. Is it clear? So, but let us take another example. Let us say I add one more point here, sorry, what is happening. I want to generate this set, these blue points, again with a line. Can I do it? So, what do I mean by generate? I want to separate these blue points from the rest of the red points. So, blue encircled points for the rest of the red points by a line. Can I do it? Why not? Because the main observation is convex hull contain this red point. Any line that can separate these points, these blue points from the rest of the red points, okay, on one, so it means that one side of the line will contain these blue points, this side of the line is containing these blue points. This is again a convex, this side, if I look at this, all this side is a convex side. Okay. So, it will obviously contain the convex hull of these points, right. But the point, the one red point in between is in the convex hull. So, this all of these points is also convex set C, and convex hull is the smallest convex set containing the blue points, that itself contains a red point. So, this convex set C will contain that red point also. So, I will not be able to separate, and it does not matter what line I take, by the way, whatever line I take, we will suffer from this problem. Okay. So, let us generalize this to higher dimension. Okay. Now, I am playing this game in RD. Okay. Let us say I have D plus 2 points in RD. Can I generate all subs? So, now in RD we cannot do it with lines. Lines does not partition RD. What do we need? So, let us say what partitions R3? Can line partition R3? No, planes. Similarly, in RD we need hyperplanes. Okay? Hyperplanes. So, if you do not know what is a hyperplane, think of we are working in R3 and we have planes. Take d equal to 3, you are not losing out on any big intuitions here, okay, or any big catch that we want to build from this. Once you learn what is an hyperplane, if you can make it work in R3, you can make it work in RD. Nothing special is happening. Okay. So, now I have a set of points in RD. The size of the set is D plus 2. And now I want to know, can I generate all subsets of these blue points? So, what do I mean by generate? Take any subset of S. I will say, so there is a term for this, it is called splitting. So, this let us call this set S. I say a set S can be split if any subset of S can be separated from the rest of the points in S by a hyperplane. Okay. This means I can split the set. For any set there will be a corresponding hyperplane that splits it from the rest of the points. Okay. Now, if I have D plus 2 points, can I split this set in RD? Can I generate all subsets of S by hyperplanes of RD? there here we will use Radon's theorem. Pardon? It should be? Should be or should not be? Should be possible. Okay, so let us do one thing. Okay, so let us in R1 let us do it. Okay. So, how many points am I taking? So, let us R1 may not be a good example, let us say R2 only. So, R2 means I will take 4 points. So, let us say I take 4 points. Can I get all the subsets of these 4 points? What is the problematic case here? Why is the problematic case? Let us say I make the set A1, I am using the Radon's theorem. Set A1 is this, the red circled points. This is A1. I make another set. This is A2. Convex hull of A1, A2 is. So, what is the convex hull of A2? The point itself, there is only one point. The convex hull of A1, A2 is intersecting. A2 is anyway like the point itself is content. So, I cannot separate. So, now again let us go back to the D+2 case in RD. Radon theorem says I can partition S into S1 disjoint partition, S1 like disjoint like non-empty partitions, S1, S2, okay, where S1 and S2 are disjoint, right, okay, good, and their convex hull intersect. Okay, good. There exists, forget about how to get it, there exists, right. There are ways to compute this, but let us say for the time being I know there exist. Okay. So, what he is asking is how to compute this partition S1, S2. That is what Radon theorem says, no? Any set, the size has to be D+2. Their convex hull, I will come to you. Okay. So, their convex hull are intersecting. Okay. Can I separate S1 from SC? Now, if S1, if I was splitting S1, that means I should, there is a way, there is a hyperplane that separate S1 from S2. Can there be a hyperplane that separate S1 and S2 given that their convex hull are intersecting? No. So, what does it mean? Sets of size D+2 in RD cannot be split, or I cannot generate all subsets of S by hyperplanes in RD, right. In terms of VC dimension, this means for a okay, I do not want to get in again, I do not want to rein in on. So, the VC dimension of this with half planes in RD is D+1. Okay. I do not want to rein in on Rajiv's punchlines, but this is something that this is being used everywhere to show bounds on VC dimensions via things like lifting map. Lifting, like we will discuss in context of convex like convex hulls, Voronoi diagram, Dillon triangulation, but these things can be used in other settings also. Rajiv will discuss these things in much more detail, but this simple observation is a very fundamental observation that is used everywhere, and Rajiv will give you many more nice examples. Okay. So, I will end this class. So, okay. So, before I end, he had a question, how do we compute the set S1 and S2? How do we compute the set S1, S2? That is the question. How? So, try to think, can I use convex hull, can I use convex hulls or convex sets somehow? So, let us assume you know how to compute convex hulls using in RD, let us say. Can you use that to get this set? That is a question, okay, to check. It is a question to think about. Okay? I end.